Hello, today we're going to learn the method of undetermined coefficients and use the superposition approach. And we're going to be applying this to non-homogeneous, constant coefficient linear differential equations. And so here's an example of a general nth order non-homogeneous linear constant coefficient differential equation. The g of x that is on the right-hand side of the equal sign is not equal to 0 when we have a non-homogeneous differential equation. The a sub n minus 1, and all the other a's, those are going to be constants. They will not have any x's in them. And the powers of y and all of its derivatives will be linear. So the process is that we have to do two things. We have to solve the equation twice. The first time, we solve the associated homogeneous equation for the complementary solutions, like we did in the previous section. So the idea is that for a moment, we assume g of x is equal to 0, and we find what possibilities there are for solutions when g of x is equal to 0. We put those together to form the complementary solution. Remember, if we're working with a second order homogeneous equation in step 1, then we should expect two solutions. And so then y sub c will be a linear combination of those two solutions. If it's third order, 3 solutions, and so on and so forth. Once we're done finding the complementary solution, then we're going to solve the non-homogeneous equation for the particular solution y sub p. But before we begin this whole process, we need to learn about how to correctly, quote unquote, guess what our particular solution might be. The book and many other books also call this a guessing process, but it's not really a random guess. It's a highly educated guess. We go into looking at g of x with some understanding about functions and their derivatives and how they behave together. Okay, so our families of solutions are only going to contain functions for which derivatives make them go away or derivatives make them repeat. So if we just think of some random functions like natural log of x, if we were to say y is equal to the natural log of x, then what would happen is y prime is 1 over x, y double prime is negative 1 over x squared, and so on and so forth. What's happening there is that the function is not repeating itself with its derivatives, and it's not going away. It's getting to the point where the denominator is getting bigger and bigger and bigger in power. And so that's not the type of function that we're going to be after. We're going to be after nice functions. And so in order to talk about nice functions, I need to give you some examples. So our families of functions that we want to work with are going to be polynomial, exponential, and trigonometric, but only certain exponential and certain trigonometric functions. What I mean by that is for exponential, we want base e exponential functions. I'm not going to work with base 2. That's not going to work for us. Trigonometric, I want only the trigonometric functions whose derivatives give us repetitions. Or we see like a cyclical behavior of some sort, like the functions don't get worse and worse and worse. And just, for a counterexample to that, imagine if y was tangent of x. Well, then y prime would be secant squared of x. Y double prime would be 2 secant times the derivative of secant, which is secant tangent. And all of a sudden, it's just getting uglier with each next derivative. And so we stop. That's not a good candidate for what we want to do. So I want to show you a couple of examples. So let's say that y was equal to x cubed. Well, notice that y prime is 3x squared. The degree went down. Y double prime is 6x. The degree went down again. Y triple prime is 6. Degree went down again. Fourth derivative, we get 0. So this is an idea of what I was talking about, where this is a function whose derivative makes it go away after a specific number of derivatives. So polynomials are good functions because over time, as we continue to take derivatives, they end up going to zero. With exponential functions, we get the same function up to a multiplier with every derivative. So here, if y is e to the 3x, then y prime is 3e to the 3x, y double prime is 9e to the 3x, y triple prime would be 27e to the 3x. Every time we take a derivative, we're seeing the same functional part, we just have a different multiplier. And so this is a nice function. With the trigonometric functions, we have to be careful. There are only two good trig functions. I brought up one of the bad ones, tangent, but there are a couple others. But we want to focus on the two trig functions for which derivatives cause a repetition. And those are going to be sines and cosines. So for an example, let's say we have y equals 2 cosine of 2x minus 3 sine of 2x. Well, if I take the derivative of that, I get back a multiplier of sine and cosine. So I get negative 4 sine of 2x minus 6 cosine of 2x. The sine and the cosine swap places because of the derivative, but that's okay. They're both still showing up. In the second derivative, we end up with minus 8 cosine of 2x plus 12 sine of 2x. So again, cosine and sine swapped places, but we're just seeing multiples of sines and cosines with each derivative. So these are good. Sine and cosine together form a family. They do not show up in the family alone. They have to come together. Okay, they're like conjoined twins. You'll always see them together. Now, in the table below, the first column is going to be examples of a possible non-homogeneous term in a differential equation. We're going to focus on just the non-homogeneous term to begin with when we guess for our particular solution. But there will be more that we have to consider, and we'll focus on that after. Okay? So the second column I've left blank for us to guess what our particular solution might be given what the non-homogeneous term is. Okay? So this table is an exercise. It is not meant for you to memorize. It is an exercise. This is a process that you should go through independently of me. Maybe you watch this video once and you see what I do, and then you shut it off and you try to do it by yourself. The idea is that you could independently figure out what a good guess for y sub p would be. All right, so let's say that our non-homogeneous term is 6x. Now remember, to the left of the non-homogeneous term, we have, possibly some a sub n, y to the n derivative, plus some a sub n minus 1, y to the n minus 1 derivative, plus all the guys in the middle, plus a1 y prime, plus a naught y equals g of x. So we're saying that y sub p should be a function so that when I take y sub p and I combine it with its derivatives, I get back 6x. Well, 6x is a linear function, so I'm hoping that my particular solution is some linear function. It would make sense that it would take a linear function and its derivatives to be added together to give you another linear function. So the family here is linear. And so my guess for y sub p would be ax plus b, where I'm using capital letters for a and b because I really want them to stand out so that I can see them very well when I try to figure out what they are. Okay. The second row says g of x is equal to 7x squared minus 3. This is quadratic. I would hope that in order to get a quadratic function on the right-hand side of my linear non-homogeneous differential equation, then on the left-hand side, I would have to have linear combinations of a quadratic function. And so that is my guess. Y sub p should probably be ax squared plus bx plus c. Notice that in the first one, where 6x was a linear term, or it's a linear function for g of x, but there was no like 6x plus a number, I didn't leave out the plus b in my standard form for the particular solution, right? I have to leave all the possibilities. So when I say that I'm going to guess a form for y sub p, I always guess the standard form. So we're going to always use the standard form for the family. Okay, so the standard form for a linear family is ax plus b. The standard form for a quadratic family is ax squared plus bx plus c. Even if g of x does not have a bx term, doesn't matter. We have to include it, okay? So then we come to g of x equals 5x to the fourth. This is a quartic function, just means it's fourth degree. And so I'm going to guess that y sub p should be fourth degree. Ax squared plus, nope, not squared, ax to the fourth plus bx cubed plus cx squared plus dx plus e. That would be my guess. Okay. The next one, g of x is equal to 13e to the 3x. This is exponential. The exponential standard form is simply y sub p equals a e to the 3x. I'm going with 3x because that's what's on the right-hand side of the differential equation, but I don't know that the actual solution has a 13 in front of it. It could be something else. So I have an unknown multiplier, a, times the family, e to the 3x. Okay, the last one on this page has a little bit more going on there. I'm seeing the 7x, and I'm seeing an exponential. 7x is linear, so I have a linear, but then it's multiplied by an exponential. Well, when it comes to the standard form, fortunately, that's exactly what we're going to set up for the standard form. Y sub p should be a linear function in standard form, ax plus b, times the exponential function in standard form, e to the 4x. But notice I didn't put another constant in front of the e to the 4x. That's because the linear function is doing that job, right? You think of like up above when g of x was 13 e to the 3x, that was a constant family times an exponential. So I just had the constant a times the exponential. In the last one, we have a linear function times an exponential, so I do a full-blown linear times the exponential. All right, we've got more. I want to make sure we get lots of practice with this. So the next one, it looks like there's a plus sign in between two terms, and so we need to handle those very carefully. We have a sum of terms in our non-homogeneous equation. That means we should have a sum of guesses as well. So in the first sum, it looks like I have a quadratic times an exponential family. In the second sum, it looks like I have a linear function times an exponential function. So it's quite literally quadratic times exponential plus linear times exponential. And that's what we do for our standard form. Now we have to be careful because as you've seen up above, I kept starting over at a, right, for each one of my guesses, but these were unique guesses for one g of x. I have two pieces of g of x, so I'm not going to let a show up twice. Here's what I mean. In the quadratic times the exponential, that part of y sub p should be an ax squared plus bx plus c times the exponential e to the 3x plus the linear standard form. Now I'm not going to start over with a. I'm going to pick up in the alphabet with dx plus e. So it's my linear times my exponential e to the 2x. Okay. Now, one thing I want to note, and right now it won't make a whole lot of sense, but when we get to it in the next page, it'll start to make a lot of sense. So since I have a sum of families, I could also say that I have a sum of particular solutions, y sub p1 plus y sub p2. And it's true, I do. I have a sum of particular solutions. I could choose to handle them each separately from each other. Okay, and more on that later. Let's keep going. G of x is equal to 5 cosine of 4x. Now, up above, I had said that the two trig functions for which derivatives cause a repetition are sine and cosine, and sine and cosine together form a family, not separate. They're like conjoined twins. They cannot separate. So when we're trying to guess a particular solution and the non-homogeneous term just has a cosine, I don't care. You got to have both of them. The particular solution will be a cosine of 4x plus b sine of 4x. Sine and cosine come together, okay? Do not separate them. I always write my cosine first and my sine second, and I remain consistent with that throughout all math classes that I teach, because if I start swapping places, I tend to lose track of my sines and my cosines. And you'll see soon when we do some examples why it's so important to keep track of your sines and your cosines. It'll make solving for the A's, the B's, the C's, and the D's a lot easier. All right, g of x, we have a linear function times a sine function. Okay, so I have linear, and that's times sine. But I'm going, remember, sine doesn't stand alone. I'm going to have a cosine, and cosine's going to want its own linear family to multiply with. So I'm also going to have another linear times the cosine of 2x. Those have got to be unique linear families for each of those trig functions. They may be like conjoined twins, but they each want their own mate. Okay, they're not going to share. So when I choose y sub p, I'm going to get a linear ax plus b times sine of 2x, and then plus a new linear function, cx plus d, times, I wrote sine and I really wanted to write cosine, especially after I made a big deal about that. And then cx plus d will be times my sine of 2x. Okay. The next one is even worse. I've got 2x, I've got e to the x, and I've got cosine of x. Okay, so I have a linear, I have an exponential, and I have a cosine of x. So remember, the cosine of x is going to have the sine of x show up as well. And so I've got something like this, a linear times an exponential times a cosine of x plus a whole new linear times the exponential times sine of x. Okay, now the exponential itself is just e to the x. That's it. So it's not a new exponential for each one. The linear coefficients will make it unique, okay, because those coefficients will be different from each other. We won't get the same linear function, and when we multiply out a linear times an exponential times the sine of x versus a linear times an exponential times a cosine of x, we'll see that each of the exponentials has got its own unique constant. All right, so our guess will need to be linear ax plus b times the exponential e to the x times cosine of x plus new linear cx plus d times the exponential e to the x times sine of x. Okay, last one looks like a sum of three things, and so remember, we have to have three individual particular solutions summed together. So the first one is quadratic, the second one is a linear times an exponential, the third one is a linear times a sine. So we should have a quadratic plus a linear times an exponential plus a new linear times the cosine of x plus another new linear times the sine of x. Okay, so the linear function in its standard form shows up 3 times, but each time it shows up, it has to be unique from the other times. Okay, so when we write this out, we have y sub p is equal to, the quadratic standard form is ax squared plus bx plus c, plus the second one is the linear times an exponential, so the linear will have dx plus e times the exponential e to the 3x. And then plus, we have a new linear, so we'll go fx plus g times cosine of x, plus the last one, we can do hx plus j. I stay away from I because it sometimes will end up looking like a 1 if I get lazy. And that'll be times the sine of x. So this one's a really horrible one. It's very long. Fortunately, we don't have to do anything with it. This exercise was merely to show you how we make our guess. So anytime you come across a non-homogeneous differential equation and you get to the part where you're trying to set up your particular solution, your first step is to look at your non-homogeneous term and decide, based on it, what should y sub p look like. Okay? Once you've done that, another thing that affects y sub p is that it must be independent from the complementary solution, y sub c. Okay? So let's look at an example where we have to take both into account. Okay? Let's say y sub c is equal to c1 e to the x plus c2 x e to the x, and g of x is 7x e to the x. What should our guess be for the particular solution? Okay, well, first we consider g of x is equal to 7x e to the x. And so this is a linear times an exponential, right? I would guess then that y sub p is a linear standard form, so ax plus b times e to the x. Okay, now consider c1 e to the x plus c2 x e to the x, which is our y sub c. Okay, now just for a moment, I want you to visualize y sub p with everything distributed. When I distribute, it becomes ax e to the x plus b e to the x. Now notice the ax e to the x is the same as c2x e to the x. The only difference is the number in front. And then, excuse me, the b e to the x is the same as the c1 e to the x. So the first guess is not independent from yc. We fix this by multiplying the particular solution that is by multiplying the particular solution by an x. Now I only want to focus on the particular solution that is associated with the repetition, okay? And what I mean by that, I'm going to take a quick pause and go up, is, do you remember up here when I said that we could break up a particular solution as a sum of particular solutions? Well, in this particular case where I have the y sub p is ax squared plus bx plus c times e to the 3x, that was y sub p1. If it is independent of the complementary solution, then I'm not going to multiply it by an x. But if the second part, the dx plus e times e to the 2x, If it has repetitions in the complementary solution, then I'm going to fix it. Okay, so I only fixed the part that's broken, but I fixed the full part. Okay, so here's what I mean by that. Second guess. Y sub p is equal to, I'm going to send an x through, and I get ax squared plus bx times e to the x. I'm not changing it to a quadratic standard form. I am multiplying the linear function by an x. There's a difference, okay? So don't start putting in a plus c, because then it will never be independent of y sub c, okay? So now if I write it out, I look at it, ax squared e to the x plus bx e to the x. Notice the bx e to the x is still the same as the c2x e to the x. So I'm going to have to, we need to multiply by another x. The whole thing, not just that one part, the whole thing was the standard form for y sub p. So my third guess, and this one will be the correct one, is y sub p is ax cubed plus bx squared times e to the x. And now I can imagine distributing the e to the x, and I will see nothing that looks like the complementary solution. And so this is good. This would be my final guess. I should say my final usable guess. Okay, now all we have done so far is figure out how to make a guess on our non-homogeneous term and how we would fix our particular solution guess if it was dependent, or I should say not independent, of the complementary solution. We still don't know what we're doing with this, so let's keep going. A few important notes before doing some examples. First, never ignore your complementary solution when trying to guess your particular solution. Make your initial educated guess, and that's based on g of x, then compare it with the complementary solution, and then fix your guess if needed until you have independence between your particular and complementary solutions. 2, if the particular solution is comprised of more than one part, as in the last example in the table, and that one part shows up in the complementary solution, then we only need to fix that one part of the particular solution, not the entire particular solution. In fact, if you do try to quote unquote fix the whole particular solution and there were parts that didn't need it, your work will not work out for you. 3, if we are given initial conditions or boundary values to solve, then you must apply these to the entire general solution. That would be the y equals y sub c plus y sub p. We would never just apply it to the y sub c, okay? Although it will be tempting. All right, without further ado, let's go ahead and work through some examples. We're going to solve the given differential equations by using this method of undetermined coefficients. And keep in mind, this is a method that we are covering in this class. There are other methods that we do not cover in this class. Do not use them. Feel free to learn about them, but I don't want to see them on a test because that is not an objective of our course. The objective in our course is to learn the method of undetermined coefficients. And so when you are given a problem to solve in an exam, you have to use this method, okay? All right. First, we're supposed to find, I should say, let's solve the associated homogeneous equation for y sub c. Okay, so what we do is we're solving, or we're going to let y equal e to the mx for y double prime plus y prime minus 6y is equal to 0. Okay, I'm not going to calculate the derivatives. We know what y prime is m e to the mx, y double prime is m squared e to the mx. I'm going to go ahead and substitute them in. So I get m squared e to the mx plus m e to the mx minus 6 e to the mx is equal to 0. I factor out the e to the mx. That leaves behind an m squared plus m minus 6 is 0. E to the mx is never equal to 0, so then I get my auxiliary equation. M squared plus m minus 6 must be 0. That will factor to be m plus 3 times m minus 2 is 0. And so then m is negative 3 and m is 2. And so finally, y sub c is c1 e to the minus 3x plus c2 e to the 2x. Okay, so that is one part of our solution. Now, the second part is we're going to guess y sub p based on g of x equals 2x. Okay, g of x is linear, so I'm going to assume that y sub p is ax plus b. That looks good. It doesn't, well, I'll go ahead and state it. So third, we'll compare y sub p with y sub c equals c1 e to the minus 3x plus c2 e to the 2x. And what you're looking for is, are there any repetitions? There are no repetitions, which means y sub c and y sub p are linearly independent. And that means that we can move forward. Okay. So fourth, we need to solve for a and b in y sub p equals ax plus b by substituting y sub p equals ax plus b, y sub p prime equals a, and y sub p double prime equals 0 into the differential equation. Okay, and just to recall, the differential equation was y double prime plus y prime minus 6y equals 2x. Okay, so we substitute everything in. We get 0 for y double prime plus a for y prime minus 6 times ax plus b. That's all going to equal 2x. So I distribute. We have a minus 6ax minus 6b is equal to 2x. And now I'm going to reorganize and combine like terms. I have one x term, that is the minus 6ax, and then I have constant terms plus a minus 6b. This is equal to 2x plus 0. And I wrote that plus 0 for a reason. I have a linear equation on each side of the equal sign. Because they're equal, that means their coefficients must be the same. So if I have a negative 6ax on the left, that should be equal to the 2x on the right. Okay, so that gives me my first equation. Negative 6ax is equal to 2x. I don't really need the x to solve this, and it's the same in each. I divide it out. I'm left with negative 6a is equal to 2, or a is equal to a negative 1/3. Okay. The next is to notice that the constant term a minus 6b on the left should be equal to the 0 on the right, which is why I wrote the 0 in. That gives me a second equation. a minus 6b is equal to 0. I should substitute the a equals negative 1/3 into the second equation. I get negative 1/3 is equal to 6b. I move my 6b over. Now divide both sides by 6, and we get b is negative 1 over 18. So finally, what I can say is my y sub p is equal to a, which is negative 1/3 x, plus b, which is negative 1 over 18. So this is the particular solution. Okay, but the question is saying solve the given differential equation. We found two things. We found a complementary solution and we found a particular solution. What we have not put together yet is what the general solution is. So then the fifth thing is to state the general solution. That would be y equals y sub c plus y sub p. Y sub c, again, was c1 e to the minus 3x plus c2 e to the 2x plus the y sub p. I get a negative 1/3 x minus 1 over 18. That's our general solution. Y is equal to that. If we had initial conditions or initial values, we would apply them to the general solution to find C1 and C2. Okay, so this problem really harped on all the different things that I brought up, or many of the different things that I brought up that are important. The comparison of y sub p with y sub c, looking at y sub p and y sub c as two separate things that come together to form the general solution, and then when we would apply any initial values if we were given any. Okay, next question. Y double prime plus 2y prime is equal to 2x plus 5 minus e to the minus 2x. Okay, so first we're going to solve y double prime plus 2y prime equals 0. That's the associated homogeneous equation for y sub c. Okay, we're going to let y equal e to the mx and substitute that in. So the second derivative is m squared e to the mx plus 2 times the first derivative, which is m e to the mx. This is all equal to 0. E to the mx is common to both, and so is m, so I'll factor both out, and that leaves behind an m plus 2. That's all equal to 0. The e to the mx is never 0, so that means that our auxiliary equation is m times m plus 2 equals 0, which gives us solutions m is 0 and m is minus 2. So then we can form our complementary solution to be c1 e to the 0x plus c2 e to the minus 2x. But 0x is just 1, so then I would simplify that and say y sub c is just c1 plus c2 e to the minus 2x. So that is one part of my full solution, is the complementary solution. I always just kind of box off my complementary solution because the particular solution is a lot more work. Okay, so second, we are going to guess y sub p based on g of x equals 2x plus 5 minus e to the minus 2x. Now what I want you to notice is 2x plus 5 all together is one linear equation. Okay, It's not two separate things. It's one family. It's linear. And then the e to the minus 2x, that is an exponential. So we have a sum of families. So when we make our guess, we expect there to be a sum in between. My first guess would be the linear standard form, ax plus b, plus c times the standard form of e to the minus 2x. Okay, now the third thing will be to compare y sub p with y sub c equals c1 plus c2 e to the minus 2x. Well, I'm looking at this, and I'm looking at this c1. I'm going to use a different color. This c1 right here looks an awful lot like this b, but b belongs to the whole linear family, right? But it's really the b that's showing up that's the same as the c1, okay? Then I'm looking at this c2 e to the minus 2x and noticing that in the particular solution I made a guess of c e to the minus 2x. So it looks like I need to fix both of the particular solution parts. Okay, so we need to fix both of the particular solution parts because both are dependent on y sub c. Okay. And so remember what that means. We're going to multiply an x through both parts. And I just want to stress this up above here. My y sub p that I guessed, because it was a sum of things, it was actually a y sub p1 plus a y sub p2. So when I'm talking about fixing both of the particular solution parts, I'm referring to the linear and the exponential. They both need a multiplier of x. So my new guess is y sub p equals ax squared plus bx, that fixes the linear, plus cx e to the minus 2x, that fixes the exponential. And now if I compare this to y sub c, I don't see any repetitions. So we're good. We can use this. Okay, fifth. Now what we're going to do is we're going to sub y sub p equals ax squared plus bx plus cx e to the minus 2x. We're also going to sub y sub p prime in. That will be 2ax plus b plus c e to the minus 2x minus 2cx e to the minus 2x. And y sub p double prime will be equal to 2a minus 2c e to the minus 2x minus 2c e to the minus 2x plus 4cx e to the minus 2x. So each time I came across that x e to the minus 2x, I had a product rule. And so that gave me a little bit more work to do. The y sub p double prime has two like terms. I will combine them. So I have 2a minus 4c e to the minus 2x plus 4cx e to the minus 2x. Okay, so we're going to sub all three of those into the original differential equation, which is y double prime plus 2y prime equals 2x plus 5 minus e to the minus 2x. Okay? All right, y double prime is going to be 2a minus 4c e to the minus 2x plus 4cx e to the minus 2x plus 2y prime. I'm going to write it right down below, okay, because this is the best way for me to see like terms more easily. So I distribute a 2 through my y prime, and I get plus 4ax plus 2b plus 2c e to the minus 2x minus 4cx e to the minus 2x. So that, just to point it out, that was y double prime, and this is plus 2y prime. Okay. When I look at combining like terms, it looks like I have a linear term. That's the 4ax. I have plus 2a and a plus 2b. Those combine. Now, my e to the minus 2x's, I have a minus 4c, and I have a plus 2c, so that's a minus 2c e to the minus 2x. And then the 4cx e to the minus 2x minus 4cx e to the minus 2x, those go away. So this is the left-hand side of my differential equation, and it should be equal to 2x plus 5 minus e to the minus 2x. So the left-hand side is y double prime plus 2y prime, and the right-hand side is my g of x. Now, I have to equate coefficients. I don't think I gave it that name before, but we're into step 6, so let's do this. We want to equate coefficients. Okay, I'm a big fan of using multiple colors while I do this, or multiple lines. So I'm going to go through and underline like terms. I have a 4ax and a 2x. Then I have a 2a plus 2b for the constants, and then I have a 5. And then finally, I have a minus 2c e to the minus 2x, and I have a minus e to the minus 2x. So I'm expecting 3 equations. So my first equation, 4ax equals 2x. The x's divide out. I have 4a is 2, and so a is 1/2. My second equation is 2a plus 2b is equal to 5. I can substitute that a is 1/2 from the first equation in. So I get 1 plus 2b equals 5. 2b is 4 and b is 2. My third equation is minus 2c e to the minus 2x equals minus e to the minus 2x. The e to the minus 2x's, those are going to divide out, and I'll be left with minus 2c equals minus 1. So c is a positive 1/2. Okay, I have all my unknowns, so now finally I can form y sub p is, let's go back and see what its form was, ax squared plus bx, so that's 1/2 x squared plus bx is going to be 2x, and then plus cx e to the minus 2x will be plus 1/2 x e to the minus 2x. That is my y sub p. My last step is to form the general solution. So y is equal to y sub c plus y sub p. Y sub c was c1 plus c2 e to the minus 2x, and then plus y sub p, which is 1/2 x squared plus 2x plus 1/2 x e to the minus 2x. And that's our final answer for the general solution. Okay. This video is already reaching 50 minutes, and that's common for this because there's a lot to go through. I'm going to stop it right now and make a part 2 that goes over the last 2 examples, only so that you can take a break, I can take a break, and then we'll come back and solve a couple much more unruly problems. In the meantime, you should be able to get started with your homework with some of these, but you might want to come back and watch examples 3 and 4 if you're struggling at all. And if you have any questions, please reach out.